Quaternions. Quaternions are a set of four real elements: w, epsilon x, epsilon y, epsilon z, with the operations of sum and multiplication, and they are represented as this. The scalar part, we have epsilon x in the direction of I, epsilon y in the direction of j, and epsilon z in the direction of k. The scalar part is w, and the vector part is epsilon, epsilon x, epsilon y, and epsilon z. We can also represent it as this, w and the vector part, where this epsilon refers to these three elements. They were created by Hamilton as a generalization of complex numbers. This is a plaque in doubling, and this is a phrase that Hamilton said about the discovery of quaternions. Let's first consider the following quaternions, Q1, Q2, and Q. The operations are the sum, where we just sum the scalar part and the vector part. The sum is associative and commutative in this case. We have now the product. The product is represented with this circle. The product is not commutative, but it's associative. The scalar part has this expression, and the vector part has this expression. We can show this by doing the multiplication term by term using the basic rules of quaternions, which I have not put here because they are not of importance for us, but you can find them in books or in papers about quaternions. We can alternatively represent this product as this, the matrix multiplication of a vector with a matrix, where this matrix is given by this. It has all the elements of a quaternion, but it's arranged in a different way. Sometimes it's easier to use this representation because you can use just matrix multiplication. The conjugate of a quaternion is the same quaternion, but the vector part is with a negative sign. And the norm of a quaternion is represented by this. It's like the norm of a vector, basically. The inverse of a quaternion is the conjugate divided by the modulo of the vector, or the norm, squared. We are rather interested in unit quaternions. Unit quaternions have unit norm. And why are we interested in unit quaternions? Because they represent a rotation of theta about an axis r. So we have the cosine of theta halves, that's the scalar part, and the vector part will be the angle, the axis, unit axis r, times the sine of theta halves. If we want to apply the rotation given by the quaternion to some vector, first we have to convert the vector to a quaternion. And so we set the vector part to the vector that we want and the scalar part to 0. Then we apply the rotation. The rotation is applied as follows. We multiply the quaternion with the vector and we post-multiply with the conjugate of the quaternion. This is just a single rotation. And then the rotated vector is just the vector component of the resulting quaternion. Some important properties of unit quaternions is that the inverse is equal to the conjugate and that the module of the quaternion product is equal to 1 because they are unit quaternions and the module remains unit. In robotics, we usually refer to unit quaternions simply as quaternions. So usually you will see that we only say quaternions, but actually we're referring to unit quaternions. Let's see an example. Find a quaternion that represents a rotation of 60 degrees about 2, 0, 0. Well, it is cosine of 60 divided by 2, sine of 60 divided by 2, and here we have the axis, but it has to be a unit axis, so I have to divide it by the module. In this case, it will just be 1, 0, 0. And this is this quaternion. Now I want to find the conjugate and inverse of this quaternion. The conjugate and the inverse are the same because this is a unit quaternion. And it is the same scalar part, and here we have a negative in the vector part, so just a negative in 0.5. Now we want to find the quaternion that represents an arbitrary rotation about the axis x, about y, and about z. So about x, we have cosine, and we have basically this, just 1, 0, 0. So sine theta halves and 0, 0 in x and in y. For y, this sign will be here in this part because the axis is 0, 1, 0. And about z, it will be the same, but we have 0, 0, 1, so sine theta half will be here in the last component. Now I want to find the rotation of at this point by an angle 60 about 2 using quaternions, and then we want to verify it using a rotation matrix. Using quaternions, first I have to find the quaternion. So I have to convert the point to a quaternion, and then I find the quaternion, which I found in the previous example. And then I apply this quaternion multiplication. So I apply this multiplication. You can operate however you want. You get this here. I'm doing the first two terms first, and then this resulting term with the last term, and I get this expression. And you see that now the rotated vector is just the vector part of the quaternion. So the rotated vector is just this part. If I use the rotation matrix, I can compute this and I multiply it with this vector here, and I get the result. And you see that both are the same. The composition of rotations use as in rotation matrices, just the product of the quaternions, but using the product of the quaternions defined before. Now I can find the axis and angle given a quaternion. Consider this quaternion Q. The axis angle associated with it are the following. This is the angle and this is the axis. These can be shown, but I'm not going to show this one. So you can find them from the big matrix expression that are originated from quaternions. However, it's more efficient to use this, a tan 2 always, instead of the arc cosine, and this r. The rotation matrix given a quaternion is this one. So in this case, the input is a quaternion and the output is a rotation matrix. If I want the quaternion given a rotation matrix, I have the following problem. Given this matrix, I want the associated quaternion, which will have these 4 components, where this sign is the sign function defined here. Let's find the unit quaternion that is equivalent to the following rotation matrix. We have to apply the formula that we just saw before. We just replace and use the sign, and here is the sign, and just replace. You can do it by hand if you want, just to check the answers. And at the end you will get that this is the quaternion.